In light of what's been done in the previous 18 videos of this series, in connection with gravitation and the mathematics of the geometry of space and time, we now want to bring it all together, with the view to then giving some logical arguments for the formulation of Einstein's field equations. Our starting point here will be to return to some very basic Newtonian gravitation. When we discussed Newton's gravity very early on in videos number 1 and 2, we came up with a number of formulae which were to do with various aspects of gravity and the gravitational field. We now want to extend those ideas a little and also bring together all that's been done so far in this series on general relativity. This will then enable us to come up with a fairly simplistic, though hopefully very helpful, derivation of Einstein's field equations. Here is a very brief resume then of those Newtonian ideas, the ones which were covered in earlier videos, and you can go back to videos number 1 and 2 for more details if that would be helpful. The gravitational field little g around a uniform isolated mass capital M was pictured using radial lines like this. The value of the field at a particular point outside of the mass M was considered to be the force acting on a unit mass placed at that point, and was written as little g using this formula. Here capital G is the universal gravitational constant, and little r is the radial distance of the point from the centre of mass of capital M. Notice the different font used for this little g to the one we used in the metric tensor. Notice also that it has been shown in this equation in bold to remind us that it's a vector, and also that it's been given a negative sign here, even though the equation is mathematically a little awkward for reasons which were mentioned at the end of video number 1. The lines of this gravitational field were actually imagined, or rather stated by convention, to have numerical significance, in that the number of lines per unit area passing through a point was considered to be equal to the gravitational field value, little g, at that point. In other words, what we call the flux density. We discussed the fact that the field lines were not drawn inside the mass on account of the fact that the mass itself is considered to be the sink for those field lines, and so the number of lines would have to be shown to decrease as the centre of mass was approached. The flux, or the total number of lines for which this mass could be said to be responsible, was calculated by simple integration of flux density with area, and was found to be minus 4 pi gm. This calculation was said to be the integral form of Gauss's equation, relating the flux of the field and the enclosed area to the total mass enclosed. However, this has to be exactly equal to what is called the differential form of Gauss's equation, which relates to the integral of the divergence of little g over the enclosed volume, which means that the volume integral of div g must be equal to minus 4 pi big Gm. In this differential form, the formula relates the divergence of the field and the volume to the mass within that volume. Furthermore, using this formula for the total mass capital M in terms of its density ρ, which of course applies whether or not the volume is homogeneous, capital M could be substituted into the differential form of Gauss's equation to produce this equation. And from this, by inspection, we can easily see that div little g must equal minus 4 pi big G ρ. And when we looked at that in video number 2, we said that this simple looking divergence equation could be interpreted to mean that at any point in space, the divergence of the gravitational field g at that point, which is a measure of the flux lines coming out of the point, or if you like, out minus in, only depends on the density of matter, ρ, at that point, as well of course as on the constants 4 pi big G. This was said at the time to be an important equation in beginning to move towards a derivation of Einstein's field equations, and we will start that process in a moment. However, as well as the gravitational field little g around a mass, which is a vector field, we also define and calculated the gravitational potential in that region, which is what we might call a scalar field. This was defined to be the amount of potential energy relative to zero at infinity that a unit mass would have if placed at some distance, say little r, from the isolated mass. This gravitational potential was given the symbol phi and was found to be equal to minus gm over r. As mentioned, this potential phi can be considered to be a scalar field which exists around the mass, and we could illustrate it as concentric spheres extending out to infinity. Going outwards, these can be considered to be increasing equipotential surfaces, the values of which are negative around the mass but tend towards zero at infinity. We also found that these two fields, the vector field g and the scalar field phi, were related by the following equation: g equals minus d phi by dr. And it should be obvious that this equation takes a scalar field phi and changes it into a vector field g by taking what we might call the ordinary derivative. You should realize therefore that this little g is a covariant vector. However, the other thing to realize is that the way it is written here relies on the spherical symmetry of the situation which we were discussing at the time. If we wanted to generalize this equation to three spatial dimensions of x, y and z, rather than simply just the radius r, we would probably write it using the grad operator of vector analysis, g equals minus grad phi. As a further reminder, this grad operator is a kind of vector operator with an x, y and z component. It takes d by dx to produce the component vector in the x direction, d by dy in the y direction, and d by dz in the z direction, giving the three spatial components of the vector g. Consequently, in this case of there being three dimensions, g equals minus grad phi is really the three-component vector, as shown here. This grad function, acting like this on the scalar energy field phi, turns it into the vector field g, which has d phi by dx in the x direction, d phi by dy in the y direction, and d phi by dz in the z direction, along with the original negative sign, of course. Many of you will realize that this could have been written using the nabla or del function, like this. However, I have deliberately avoided the use of this symbol throughout these videos, as it can often also be used for the covariant derivative and can be confusing for some. So, for the Newtonian situation, we have these two important equations: div g equals minus 4 pi g rho and g equals minus grad phi. If we now substitute this into here for the gravitational field g, the minus signs disappear and we get this: div grad phi equals 4 pi g rho, which is essentially this. The bracket of this represents the vector g, hence the three components in the x, y and z directions. And here, this vector g is being acted upon by the div operator, which is really the same as the grad operator, a vector operator. But of course this time it's acting on a vector. In fact, it's a kind of dot product with it. This action then produces a scalar. The dot product div grad of phi has produced three scalar terms which are added together, and you'll realize that each of these is a double differential because the vector operator has been applied twice. They're not just squares of the differentials. The operators don't simply multiply, they have a differential action and they act on things. Once again, you'll often see this written using the del or nabla operator like this, but as I say, I'm trying to avoid the use of that symbol in these videos. Now, although this equation is exactly the same as we had before, div g is minus 4 pi big G rho, and simply says that the difference in the field lines coming out of a point compared to those going in only depends on the density of mass at that point, it shows it in a way which suggests that we have a kind of Newtonian field equation. Mass density, rho, on the right-hand side affects the geometry of the measurements of what we might call the gravitational potential field phi on the left, and vice versa. And if we now look at a particular mass distribution in space, we can perhaps see it more clearly. Let's take the mass present to be at the centre of the system, and for the moment we'll go back to some sort of radial components, And let's assume that the metric for it is the Schwarzschild metric. Now, I don't mean to suggest that the mass is extremely large, like a black hole. It's just an ordinary kind of mass which we will describe by the Schwarzschild metric. I suppose we could say that c squared is so large in our Newtonian approximation that we could put these terms equal to -1 and +1. But we'll keep them in like this, even though the correction term is extremely small in this particular case. This will allow us to move to general relativity more easily in a moment. Let's focus then on the component in the top left corner, G00. This can be written like this, minus with a bracket 1 minus 2gm over c squared r. Or if we ignore the negative sign in front of it, we can write it like this. In some ways it can be said to be legitimate to drop the sign, because instead of taking the metric from this kind of equation for the space-time interval ds squared, where time part is negative, we could easily well use this d tau squared, where the time part is positive. But in any case, the signs will sort themselves out later, as you'll see. It is just more convenient here to have G00 in the positive form. The next thing to realize is that in this spherically symmetric system, we can say that at any point around the mass, phi will be given by minus gm over r. And so G00 can be said to be given by this expression, where we've simply replaced minus gm over r by phi. In which case, we can now rearrange this and write phi as this. If we now take this expression for phi at a point in space, in terms of the G00 there, and substitute it into our Newtonian field equation, formulated in x, y and z coordinates, we will get an equation for the double differentials of G00. Notice that in taking these second differentials of phi, the constant part of phi, the c squared over 2, has disappeared, and we've been left with the double differentials of G00, as well as the extra factor of 2 over c squared. Even more than before, this relationship perhaps illustrates some kind of Newtonian field equation. Mass density on the right, and aspects of the metric on the left. And it came about because we took a space, or rather a metric, which was not quite flat, not quite Minkowski space, or rather not quite the Minkowski metric, and worked through the Newtonian equations. In other words, in the time version of the space-time interval, instead of the first two terms being something like this for the Minkowski metric, we allowed for the slight perturbation of the time term from gravity and used this for the Schwarzschild metric. And it is this slight perturbation which just might almost be the reason for the apparent force of gravity in Newtonian gravitation. From playing around with ideas like these, which we're suggesting illustrates at least some kind of link between matter and the geometry of space, Einstein began to formulate his general theory of relativity. This equation here, although based on Newtonian gravitation, is couched in such a way that it hints at this basic idea of Einsteinian gravitation, which John Wheeler famously put like this: space-time tells matter how to move, matter tells space-time how to curve, meaning, if I put it the other way around, that the mass on the right-hand side distorts the geometry on the left-hand side, and the geometry on the left-hand side affects the geometric measurements made on mass on the right-hand side. We now want to take this Newtonian type equation and see if we can appreciate a little of how Einstein developed his general theory of relativity. That theory would not involve the concept of force of gravity and objects being pulled or pushed into new positions. In fact, all freely falling objects would be considered to move along geodesics in space-time, and it would be the use of the metric tensor in measuring that space-time which would suggest that objects had been affected by so-called forces. So along with the whole concept and mathematics of Riemannian geometry and geodesics, which we discussed in video number 8, a simplified version of Einstein's argument goes something like this. This Newtonian equation relating space-time and mass is helpful insofar as it goes. However, If there is to be a more useful equation that links matter to space-time, then that equation must not depend upon the frame of reference in which measurements are being made. The equation, if there is one, must hold in all frames of reference. That basic requirement means that the equation will have to be a tensor equation. Why do I say that? Well, one thing we've learned about tensors, whether rank 0, rank 1 or rank 2, is that they do not change if you tinker with the measuring system. The measured values that you get might change, but by using the metric tensor and the mathematics that we've discussed, you can always make compensation for the changes in the metric. You can work out what's really going on, even if your measurements show deflections, slowing down, speeding up, or whatever. Any sensible field equation, therefore, must be a tensor equation, and it must have something to do with the geometry of spacetime on the left, and something about the mass density in that spacetime on the right, or rather, on account of the fact that mass and energy are equivalent to one another, it needs to have something about the energy density in spacetime on the right. But what kind of tensors should make up any new equation? What kind of tensor should be on the left for geometry, and what kind of tensor should be on the right for mass energy? Well, in our deliberations, we've only really ever discussed rank 0, rank 1, and rank 2 tensors, which are scalars, vectors, and dyads. If we consider these one at a time, we can say first of all the scalars are just numbers. They have no indices, but simply have one value at each event in spacetime. A simple scalar equation would not be very helpful as a field equation. Vectors have one index and therefore have 4 components in 4-dimensional spacetime, and that means there would be 4 values or 4 numbers at every event in spacetime. However, in all the work we've done so far, spacetime seems to require tensors of rank 2, or what are called dyads. Such tensors have 2 indices, and they therefore have 16 components in spacetime, 16 values at each event in spacetime. The metric tensor is a typical example of that, and is bound to figure in any new theory. Excepting then that we need a rank 2 tensor equation which will relate geometry and curvature on the left, say, to mass energy density on the right, we need now to think about what each side should look like. We'll first think about the right-hand side, the mass energy part of things. In an earlier video, number 18, we discussed an obvious candidate for the mass energy density at a point or event in space-time. It was called the Stress-Energy-Momentum Tensor. If you recall, we had started thinking about this by first looking at the energy-momentum 4 vector. We then took the derivative of each of its 4 components with respect to each permutation of 3 out of the 4 space-time dimensions, and that gave us this rank 2 tensor. The colouring here identifies the various parts of the tensor, and these were considered to be densities of one thing or another, or fluxes, or flow of those things, or even, in some cases, a kind of pressure or stress. It would seem that any or all of these things would be likely to distort space-time, and not simply mass or energy. Using the metric tensor to do the conversion, this whole thing was finally written with lower indices, in other words, in covariant form, as T mu nu lower. And we can show it like this, with the various component parts identified once again by these colours. This whole thing, you recall, is a symmetric tensor. And so, for example, this equals this. And so we can talk about these 2 components as being either the density of the x1 component of the momentum at a point in space-time, or the energy per unit time passing through a unit area in the x1 direction at the point. Same thing. The x1 momentum density is the same as the energy flux in the x1 direction. Similarly, these 2, which are equal to one another, can either be thought of as the flux of the x2 component of the momentum in the x3 direction at a point, or the shear stress from a force in the x3 direction on the area in the x2 direction at the point. They're identical to one another. You can refer to the last video in this series, number 18, if you need some revision on this, but we don't really need the detail here. This whole stress-energy-momentum tensor is the obvious candidate to use instead of the simple mass density rho of the equation we had for Newtonian gravity. For one thing, it won't simply be mass which will be able to curve the space-time. There has to be much more on the right-hand side of this equation, including energy, momentum, flow of mass, flow of momentum, pressure and stress. And for another thing, we need a rank 2 tensor. So let's put the stress-energy-momentum tensor in instead of rho, and for the moment we'll leave the left-hand side blank. You'll notice that I've left the constants in as before, and we'll sort out whether these are correct later when we compare our final equation to Newton's equation in the Newtonian limit, if you like. More importantly, for the moment, what exactly should we put on the left-hand side? It obviously has to be a symmetric rank 2 tensor in order to match what's on the right-hand side, and in the way we've chosen to write things, it will have to have 2 covariant or lower indices. On top of that, it will almost certainly have to contain the metric tensor and its derivatives. Even the contrived Newtonian equation contained double derivatives of g00, and we would expect the left-hand side here to be much more complicated and contain aspects of all 16 components of the metric tensor, not just g00. However, for the moment, let's put this left-hand side in as an unknown tensor and label it g mu nu. This g mu nu is known as the Einstein tensor. And at this stage in Einstein's deliberations, he knew that he probably had the right-hand side of his equation about right. And he knew that this capital G mu nu on the left-hand side would have to be a rank 2 tensor, which was all about space-time and its curvature and how it's measured. But what exactly should it look like? Well, the likelihood is that it would probably contain the metric tensor and probably some Christoffel symbols, as they contain derivatives of the metric tensor, and they're all to do with the distorting of space-time. Also, the way the equation is formulated, with the mass-energy part of it on the right and the geometry part on the left, means that this left-hand side, capital G mu nu, is all about geometry. And so we'll have to deal in some way with curved space, or rather, the way curved space is measured. That means it will probably have to include a curvature tensor of some sort as well. But what exactly is to be the makeup of this capital G mu nu? Well, the standard way to discuss and introduce this, and in all likelihood the way Einstein tackled things, is to ask the question, what things have we got available? What geometrical kind of things do we know about and have which can describe space-time and its curvature and could take the place of these things in this simplistic Newtonian equation? Here are some possible candidates. The metric tensor, little g mu nu. The Riemann curvature tensor, r rho sigma mu nu. The Ricci tensor, r mu nu. And the curvature scalar, r. Now, of course, the Riemann curvature tensor obviously can't be part of the Einstein tensor, capital G mu nu. As it stands, it's a rank 4 tensor, and the left-hand side of the equation must agree with the right-hand side, meaning that the Einstein tensor, capital G mu nu, must be some sort of rank 2 tensor, and in the way that we've been writing things, it must have lower indices. Let's therefore get rid of the Riemann tensor, and that leaves us with these 3 options as starters for our left-hand side. Now, you may at first think that the curvature scalar r is no good either, but of course it's just a number, and so it could be a multiplier of some other tensor of rank 2 within the equation, so we'll keep it in as possibly fitting in somewhere. As a reminder, here are the 3 things that we presently have available in a bit more detail. Firstly, the metric tensor. Hopefully we are reasonably comfortable with this. It is symmetric, and it's shown here with the repeated components in red, leaving 10 independent components altogether. Secondly, the Ricci tensor is also rank 2 and is symmetric. As a further reminder about the Ricci tensor, each one of the 16 components is calculated by contracting some of the Riemann curvature tensor components and adding them together. Furthermore, the old Riemann curvature tensor is given by this expression, where the formula for the Christoffel symbols is this. So you can probably appreciate, even without going into the details, that there would be derivatives of the metric tensor alongside the metric tensor itself if the Ricci tensor is part of capital G mu nu, and that's just what we want. And thirdly, the curvature scalar R is given by the sum of the contracted terms of the diagonal of the Ricci tensor, and is just a number. Again, you can go back and look up how these things were derived in video 17 if you wish, but we don't really need the details, as long as we have some sort of general concept of what each one is. What should be clear from all this is that firstly, if we use the metric tensor in the Einstein tensor capital G mu nu, then it will contain lots of values of its components. And secondly, if we use either the Ricci tensor and or the curvature scalar in it, then it will have lots of first and second derivatives of the metric tensor, as well as squares of the first derivatives, which come about from the squares of the Christoffel symbols. So how do we make something out of these three things which just might be appropriate for the Einstein tensor capital G mu nu? And then, of course, how do we check whether or not what we've produced is in any way likely to be valid? Well, the answer to the first question is that we guess. We suck it and see. We try this and that. Then once we've guessed something, as a first check, we test for continuity. If the stress-energy tensor on the right-hand side obeys the continuity equation on account of energy conservation and the like, which we showed that it did, then anything on the left-hand side must also obey the continuity equation. So let's do the guessing bit first, and then we'll talk about how to test for the validity of our suggestions using the idea of continuity. Although there are many ways of mixing up these three things to produce an overall tensor which has rank 2, and which we could then try out for capital G mu nu, the most obvious two things are the Ricci tensor itself, R mu nu, and the metric tensor G mu nu multiplied by the curvature scalar R. If you think about it, each of these two things has elements of the original Riemann curvature tensor in them. And so they not only contain components of the metric tensor and its various derivatives, but they also are all about the curvature of space-time. In other words, we could try simply the Ricci tensor R mu nu for capital G mu nu. Or we could try the metric tensor multiplied by R, and in each case simply see how things work out. They will each separately test our basic idea that the mass energy density on the right-hand side distorts the geometry on the left-hand side, and the geometry on the left-hand side affects the geometric measurements made on mass on the right-hand side. Our test for validity for each of them, the first thing that they must satisfy, will be whether or not they obey the continuity equation. So for this suggested equation, here is the stress-energy-momentum tensor T mu nu, which we spent some time thinking about in the last video, number 18. And on account of the conservation of energy and momentum, we said that this stress-energy-momentum tensor, T mu nu, must obey the continuity equation, which was written like this. This equation, written here using the summation convention, was shown to represent four equations in four-dimensional spacetime, and we can highlight the tensor components in accordance with the pattern of colours that we had earlier. If you recall, the truth of this continuity equation, or these equations for T mu nu, will ensure that if the energy or momentum density at a point changes with time, then there must have been a flow or flux of that energy or momentum to or from that point in some direction or other. And we said that we must therefore assume that T mu nu obeys the continuity equation or equations. As a consequence of that, it should seem reasonable that if T mu nu on the right-hand side of our suggested field equation obeys the continuity equation, which it definitely does, then whatever we choose for capital G mu nu on the left-hand side must also obey it, as these are just constants of multiplication. Therefore, as we initially consider each of these two fairly basic possibilities for G mu nu, the first thing we need to do is to check that they each individually obey the continuity equation. If they don't, then they cannot be used, as they are, for the Einstein tensor capital G mu nu. So first of all, therefore, we need to see whether this derivative of the Ricci tensor equals 0. And then secondly, whether this derivative of the product of the metric tensor with the curvature scalar equals 0. It seems reasonable perhaps that at least one of these needs to be okay in order to give us a chance of finding something to write down for capital G mu nu. Now in video number 7 we discussed the formula for the covariant derivative of the covariant components of a simple vector, and it was given by this equation or equations. In four-dimensional space-time this will produce 16 equations for the four components of the vector, each differentiated with respect to the four dimensions of space-time. Each of those equations will say that the covariant derivative, the proper derivative, is equal to the measure derivative from the metric minus the correction or connection factor of the Christoffel terms. Now, given that we're dealing with tensors with two indices and not just a simple vector here, you can probably imagine that applying this derivative formula first to the Ricci tensor and then to the product of the curvature scalar and the metric tensor by the product rule is a fairly messy task. But something we probably could do if we wanted to spend time on it. It needs a few tricks, such as remembering that the covariant derivative of the metric tensor is always 0, but it's not mathematically difficult. It just takes a lot of time and patience and accuracy of working. However, instead of working through these calculations, we'll simply state what the answers come out to be. Here are the two results for the covariant derivative of the Ricci tensor and the covariant derivative of the product of the metric tensor with the curvature scalar. Looking at the result for the first one, the answer comes out as essentially the product of two terms. However, this G mu nu is obviously not 0, and neither is dr by dx mu, the rate of change of the curvature scalar r with some direction. That won't generally be 0 either. The conclusion then from this derivative is that this r mu nu term does not satisfy the continuity equation. Its covariant derivative is not equal to 0, so it's not a useful candidate for the Einstein tensor capital G mu nu. Okay, so what about the second one, G mu nu times r? Well, the result for the covariant derivative of that one is almost the same as the first, except that it doesn't have a multiplying factor of a half. This isn't guaranteed to be 0, and neither is this. In other words, we can say that the term G mu nu r is also not suitable for the Einstein tensor capital G mu nu, for exactly the same reason, namely that its covariant derivative is not 0. In our attempts at making a sensible set of field equations, both of these suggestions, r mu nu and r times G mu nu, fail at the first hurdle, the test for continuity. However, if you look again at the results for the two covariant derivatives, you can see that the first result is half of the second. And that means that if we take capital G mu nu to be equal to this mixture of the two original tensors, namely r mu nu minus half r times G mu nu, it would mean that when we take the covariant derivative of this, we get this with a half in front of it from the derivative. And when we take the covariant of this, we get this, but it already has a half in front of it, so the whole term is this, exactly the same as the first term, and it has a negative sign in front of it. In other words, we get the result equal to 0. This means that if the Einstein tensor capital G mu nu were to be made equal to this expression, r mu nu minus half G mu nu times r, it would at least satisfy the continuity equation and is at least a suitable candidate for the geometry side of the field equations, which would then become this. Now, don't let this c squared bother you. You will have seen Einstein's field equations with a c to the fourth in it here, and that will come in a moment. This simplified derivation is okay so far, and even though it may have seemed rather haphazard in the way things were approached, it turns out that this general form is really the only way to relate the geometry and curvature of four-dimensional space-time to the mass-energy-momentum density within it. However, there could of course be a constant multiplying factor needed somewhere, and so we probably ought to write the equation at this stage at least like this, where a constant k has been added to the right-hand side, although it could equally well have been added to the left-hand side. We're almost there, but not quite. In order to find what this constant k is, we can check the results of this whole equation when it is evaluated in the Newtonian limit, and that should allow us to choose a value of k so that the equation agrees with the Newtonian equation which we had earlier, which was this. So basically, we need to evaluate this equation for the 0, 0 components of everything in it in the Newtonian limit. And of course that's not quite so easy. These are 10 independent equations, or rather 16, and they are non-linear second-order partial differential equations which are linked or coupled to one another. Doing the calculation is tedious and involves making a number of assumptions and working through the mathematics of what we might call the summation equations. You'd probably start by multiplying this whole equation by g mu nu upper, and then evaluating what that would do to the three tensors in the equation. The rest of the calculation would proceed on the assumption that in the Newtonian limit the gravitational field is weak and unchanging, and also that we have no movement of any mass, no momentum, and hence no pressure or flux in the energy-momentum tensor T. It will effectively become rho. We'll also assume that the spatial part of the metric tensor is that of flat space, all ones and zeros. Only g00 is changing, so only g00 will appear in the calculation. And all of that means that the way we've formulated things, this equation with the k in it, once evaluated in the Newtonian limit, becomes, after a lot of hard work, this. This is the prediction from what we have so far for Einstein's field equations, and if we now compare this with the Newtonian result, which we derived from the div-grad discussion, we can see that the constant k must be 1 over c squared, meaning that our initial formulation of Einstein's field equations needs to have an extra c squared on the bottom on the right. So instead of this, it needs to be this. We now have a c to the fourth on the bottom instead of a c squared, and if any minus sign has been lost anywhere in the earlier discussion, we would also have found that correction here. And these are Einstein's field equations, all 16 of them. If the extra c squared bothers you, I suppose a very handy and simplified way to think of it is to say that Newton's equations used rho, whereas Einstein's used rho c squared in the t00 position. The latter dealt with energy rather than simply rest mass, so in trying to bring the two together, one is bound to have to divide by an extra c squared to get things right. More to the point, it is important to realize that the T mu nu of Einstein's field equations is more than simply the mass energy density rho, or even rho c squared. There will be some situations where mass is moving, where mass density is shifting, and mass densities and velocities could be very high. The particular simplification that we've just considered, where we essentially use simply T00 of the energy-momentum tensor and equated it to rho c squared, was only to discuss the Newtonian situation of low gravitational fields and slowly moving masses. More generally, T mu nu will be a tensor with 16 components, or 10 values, at each point or event in space-time, and it can be thought of as the source, or perhaps we should say the sink, of the gravitational field at each event. It is the thing which causes the curvature of the space-time, and it's not just the mass per unit volume, or even the energy per unit volume. As we said when we discussed the Stress-Energy-Momentum Tensor in video 17, it also involves the flux or flow of energy at the point, which can also be interpreted as the momentum per unit volume, and this energy flux or momentum density also contributes to the gravitational field and curvature. And there's even more than that in there. We can say the same about the various kinds of force per unit area, which are also components of this tensor. If the rate of change of any momentum of any mass is parallel to some area vector, then we have to think of it as a kind of pressure. If it's perpendicular to an area, meaning along the face of the area, then it is effectively a shear stress. All of these parts of the stress-energy-momentum tensor will contribute to being the source, or rather the sink, of the gravitational field at any point in space-time, and hence will cause it to become curved. However, it must be stressed that by far the greatest contribution to any curvature will usually be from the mass energy density, the component in the top left-hand corner, the T00, unless velocities are incredibly high and approaching the speed of light. We touched upon this earlier in converting mass density to energy density, which is what that T00 is. We have to multiply the speed of light squared, and that is a very large number. It means that when we're dealing with situations where velocities are non-relativistic, let's say fairly slow, then the other components of the tensor, energy and fluxes, momentum fluxes, pressure, will be extremely small compared to T00, and so those other contributions can often be set to zero, simplifying, at least to some extent, the equations that need to be solved. Okay, so we've now shown how Einstein's field equations can be considered to come about, and we have, I hope, some concept and appreciation of what they mean. We are not, however, going to attempt any mathematics with them. Far too complicated. Instead, at this point, it might be worth a quick word about gravitational waves. In Newton's theory, it had to be assumed that if a mass changed in some way, say its position, then the effect on the gravitational field around it was instantaneous, everywhere, even out to infinity. And that would mean, for example, that if the concentrated mass at the centre of this picture somehow moved up and down like this, then the field lines would follow it rigidly and instantaneously, as we see here. There will be no delay in the change of the field some distance away, any distance away, even out to infinity. As the mass moved, the gravitational vector field little g would change everywhere at that instant. We could also illustrate that kind of thing, of course, not only with this picture here of the gravitational field lines, but also with a depiction of what we might call the equipotential surfaces around the mass, the scalar field values of the potential phi. They would be shown as concentric circles in this two-dimensional picture. Once again, however, in the Newtonian interpretation, we would have to say that if the mass at the centre moved around, then the lines representing the gravitational potential phi some distance away would change at that instant. There would be no delay. All of that would mean that information about the movement of the mass would have been transmitted to all points in space instantaneously. Relativity, on the other hand, teaches us that information, like the changing position of a mass, cannot be communicated instantaneously over distances within space, but rather the gravitational field would surely have to bend and twist as the mass producing it changed its position, and that would give rise to some sort of wave. The usual illustration suggested for that is where two black holes or neutron stars are in orbit around one another. This is illustrated here as a perspective view, where we're looking at a slight angle from above at two concentrated masses, one of which is shown here as being larger than the other. The equipotential field lines are more or less spherical at large distances away, although obviously they look elliptical here because we're viewing them from an angle. Closer to the masses, of course, these lines distort somewhat. A given gravitational potential line close to the small mass will be further away from the large mass. The Newtonian picture of this rotation would be that as these two masses rotate around one another, all the lines would be rigid and would turn instantaneously, even out to infinity. However, general relativity says it must be more like this. This two-dimensional surface picture is an attempt to show what the ripples in the gravitational field might look like. It gives a sense of the gravitational waves that might emanate from two large rotating masses. Now, analysing this kind of situation close to the masses, using Einstein's field equations in order to show the formulae for those waves, even with a load of simplifying assumptions, would be horrendously difficult. A little easier, but still very time-consuming, would be to think about weak gravitational waves travelling through free space, far, far away from any other masses. For instance, once these ripples, these waves, are far away from the masses which produce them, they will become weaker, and they will be travelling through space where there was no mass, and so would perhaps be more amenable to analysis. To do that, to find a solution to Einstein's field equations when there is no mass or energy around locally, would mean first taking these field equations and then putting the stress-energy-momentum tensor T mu nu equal to 0, which would then give this equation, or if you like, this. Taking this equation, or rather these 10 equations, and making another load of assumptions and approximations would allow us to find wave equation solutions for the waves travelling through this free space. However, even that would be a long exercise and probably not worth spending time on in these videos. You can look that up if you wish. Suffice to say, as such gravitational waves travel through space, they would stretch and compress that space in the directions at right angles to the direction of the travel of the wave. If you imagine a sphere through which the wave passes, and if you look at it head on as the waves come at you, then that stretching and contraction could be illustrated like this, though this picture is wildly exaggerated. The changes in shape would be minuscule in practice. While any kind of calculation for simple gravitational wave motion in free space is probably not worth spending a load of time on here, it might be worth at least mentioning the early LIGO experiment of 2015 in the USA. This had been set up in order to try and detect gravitational waves originating from some very large accelerating mass in the distant universe. Such waves might come from two closely rotating black holes, or perhaps from the collision of two neutron stars. The waves would stretch space in one direction, perpendicular to the wave motion, and compress it in the orthogonal direction, in the oscillatory way illustrated a moment ago. Such waves would be incredibly weak by the time they reach the Earth, and almost impossible to detect. The LIGO experiment consisted of two 4-kilometre-long perpendicular arms used as a massive laser interferometer, and the minuscule changes in any expansion or contraction of space was measured from changes in the interference pattern from the two return laser beams. And in order to try to eliminate any spurious effects in the detection of such signal, the apparatus was replicated in a second experiment almost 2,000 miles away, and each of the experiments looked independently for any weak gravitational signal. Prior to the signal that was seen in 2015, a lot of work had taken place not only on the experimental side in order to be sure of the detection of such weak signals above any noise, but also on the theoretical side in order to interpret such a signal. Early on, theoreticians had set about trying to find solutions to Einstein's field equations for various different types of possible scenarios, neutron stars, black holes, and the like. As you can imagine, solving equations like this for two extremely large masses colliding or rotating around one another would be absolutely mind-boggling. Powerful computers and numerical methods were used, and it led to various predictions as to what different-looking signals would likely be due to. Then in September 2015, both groups of experimenters, almost 2,000 miles apart, remember, detected virtually identical-looking signals at the same time. Here's a sketch showing the strain in the apparatus against time. Strain is essentially a fractional measure in the change of shape, and in this case the maximum strain or fraction was of the order of 10 to the minus 21. Essentially, this sketch is showing the stretching and squeezing of space as the waves pass us by in less than a second. And from the modelling that had been done around different scenarios, this particular shape for the signal was interpreted, with some confidence it was claimed, as being due to two black holes rotating around one another, faster and faster, getting closer and closer until they become one black hole of greater mass. The signal does seem to imply that the frequency of rotation increases as the two masses come closer together. At the same time, the amplitude of the wave increases, and all of that continues until, it would seem, the singularities coalesce and everything settles down. Finally, I suppose it would be remiss of me to end this series of videos without mentioning something about the cosmological constant. You've almost certainly seen this within Einstein's field equations, which, rather than being written like this, which is what we derived, are often seen in this form, with this extra term, a constant lambda times the metric tensor g mu nu. This constant lambda is known as the cosmological constant, but why has it been inserted into the equations? Well, in order to do this topic justice, we would really need another fairly lengthy series of videos on cosmology, which would discuss the ways in which we might apply the bare Einstein field equations to the whole of the universe, to the cosmos, rather than simply to a limited region of space around a mass or whatever. We would also, of course, have to include all types of mass and energy within the universe. It wouldn't simply be a case of thinking about the various masses present in galaxies. We'd need to think about energy, momentum, and even the pressure that we've talked about in the Stress-Energy-Momentum Tensor, treating the whole of the universe as a single entity. The next and final video in this series will try to do just that, to compress what really should be a detailed course on cosmology into a short video. It will cover the basic ideas which involve the Freeman, Lemaitre, Robertson, Walker metric for a particular model of a universe which might be expanding, and it will make the assumption that the whole of the universe can be considered to be some kind of perfect fluid. Now, inevitably, it will not give rigorous explanations or cover some of the fascinating detail that you'd get in an in-depth course on cosmology. Hopefully, however, it should give a persuasive explanation and reason for the presence of the cosmological constant in Einstein's field equations when applied to the universe as a whole. This video number 19 has at last tried to explain and justify Einstein's field equations, but of course they are missing the cosmological constant. In the last video in this series, number 20, we will consider the ideas of a static, expanding or contracting universe, and that will take us to a very brief look at the Friedmann equations to justify the cosmological constant.